small one, but now I'm scared. Looking at you, trying to see your stalling. Ooh, one hesitant step ahead. You're not a small one, but now you're scared. Looking at you, trying to see where you're crawling out. Emergency, oh.
We are going to continue with Andre Arko, and yeah, he's an open source guy of sorts, I guess. Currently being the main maintainer of Bundler, which is probably his biggest task, I guess so. And sorry. Okay. Yes. Okay. So please give a warm welcome to Andre. And yeah, have fun with the rest of the conference.
So my talk is about development and how it is not the same as production, but probably not the way that you think I'm going to talk about that. So first, I'm Andre Arko. I am indirect on all of the internet things. I work at Cloud City, where we make web applications mostly using Ruby. I am also a lead developer of Bundler. That's a lot of fun. It's hard, but it's a lot of fun. So this talk in particular is about production and the problems that you can run into in production, and how the way, like, basically, you know, like, as developers, we spend all of our time working on our applications in development environments, right? Like, that's the whole point. We are developers. We use our laptops, we add new features, we debug bugs, we test things, right? Like, and in none of those cases is our code actually running in production and being used by users. But if you added up the number of minutes that your code actually spends running, rather than the number of minutes that you spent staring at your running application, the vast majority of the minutes that your code spends running are actually going to be in production, not on your machine in development. And the number of minutes where your code running and the outcomes actually matter are, of course, almost entirely in production, because that's where there are actually people using your program to do whatever it is that they care about that is hopefully paying your salary. So in order to kind of talk about the ways that production and development diverge, I'm basically going to talk about the pieces of that are not obvious until after you've had things go wrong a lot of times over a very long period of time. So to start with, I'm going to talk about metrics. This talk basically breaks down into like 3 sections that should maybe each be an entire talk by themselves, but I really want to talk to you about all 3 of the things because I feel like they're really important, so we'll see if I can squeeze them in. Metrics are really important. Metrics are basically how you know what is happening in your application while it's running in production, because you're not sitting there using your website in production mode 24/7. Metrics, once you have them up and running, kind of give you this impression that you actually know what is going on in production. But metrics, especially if you make web applications that use Ruby, and especially if you don't hand roll your own metrics, but even probably if you do, this actually probably just means averages. And averages have this really interesting, sorry, I should explain averages. So New Relic, for example, which is the most popular way to instrument a Ruby application because it doesn't take any work, instruments all of your stuff, collects statistics about all of your stuff, and then calculates averages, throws away all of the data that isn't averages, and sends the averages to the server to be put into pretty graphs for you. This is why that's bad. Turns out brains are pretty weird. You probably don't actually understand averages. I definitely don't understand averages. Like, you see an average and you think, oh, here is the average number. That means that the entirety of the distribution of the things that were averaged together probably looks like this, right? This is a normal distribution. Average, that's in the middle, and about half of them are above that and about half of them are below that, right? No. Unfortunately not. So I'm going to give you like a mini graphical demo of how brains are broken about averages, and hopefully that will convince you. So here is a bunch of, this is like, in this particular example, this is like timing distributions across 35 different machines. And the height is the number of events that took that long, and left is short and right is a long time. So here's 35 different machines. As you can see, they all have different distributions. None of the distributions look even vaguely normal. And each one of the individual machines has the average for that machine marked with a little black line. So in order to try and illustrate what the average actually means, I'm going to align them all on the black line, which is the actual average across all of these machines. That is the actual average, which is the number that you would get if you were looking at an average across all of these machines. I don't know about you guys, but the fact that 90% of the number, like of the events on that graph, are significantly to one side of the average freaks me the hell out. My brain would never have gone here if I had seen just the number that represents the black line, right? Like, so kind of the moral of that part is averages mask problems, right? Like if a graph that looks like that is a problem for you, you wouldn't have actually known if all you had was the average number. This is averages. Don't do this. Graph, if you can, like actually make graphs like that graph the entire distribution so that you can look at the distribution and be like, oh, this is not a normal distribution. This is this kind of distribution or that kind of distribution, because it's almost never the thing that you would think when you see the average. If you can't graph the entire distribution, which I totally understand is not always feasible, you can get a reasonably good proxy for graphing the entire distribution by just adding on top of the average, which is the mean, add the median and the 95th percentile, and graph all three of them on a single graph. I should probably have gotten an example of this. That would have been cool. For Bundler API, which is the like web service that powers bundle install, we do this, and it is way, way more helpful to see that like the 95th percentile requests have just shot up to 3 times as long as they were 5 minutes ago, but the average basically didn't move. Like, that's really important to know. Something has gone wrong. Something's probably going to break if this state continues, but I wouldn't have ever figured it out from the average. There's one pretty related problem, and that is aggregates, which is basically another way of saying averages, but across multiple machines. It has all of the same problems. Like, we have, say, a dozen machines running the same, like all running app servers for our web service. If we see a single line that denotes the load across all 12 of those machines, that average number is going to be wildly misleading, because some of those machines will have no load and some of those machines will have insane load, and they will average out to right in the middle where it seems totally reasonable. The statistician joke about averages is that the statistician puts her head in the oven and her feet in the fridge and says, on average, I'm perfectly comfortable. So to solve this kind of problem, the answer is just like breakout graphs. If you're using a system that does metric reporting, like where you are reporting the metrics, like Librato is a really good example of this, you can make a graph that is an aggregate, and that's fine. Like, you can see certain kinds of problems on that graph, but have another graph that actually has individual lines for every node, because when one of them goes crazy, you'll actually be able to see it, because it's going to be like this huge outlier far away from all the rest of the lines, even though the average isn't going to change significantly because all the other machines are outweighing it. Relatedly, you should be alerting on the broken out graph, not on the aggregate number, because the average is not going to break your alerting threshold while 2 of your boxes have gone insane and are throwing away all of the requests that go to them. We actually had this happen. There was a bug in the web app server that we were using that meant it would lock up and accept requests forever without ever responding to any of them ever again. And on average, we were doing pretty good. But every, every request that got routed to those 1 or 2 app servers that were locked up would just never get a response and would time out. Right, yes. Alerts on aggregates are probably too late. Like, by the time the average has skewed far enough that you got an alert notice, like, chances are high that everything is broken instead of just some things being broken. Okay, so metrics. That's important. Think about that. Let's move on. Servers are like a whole new kind of problem. You probably have no idea what's actually going on your servers. Really, I'm not kidding. Like, yes, you know that there is a server, right? But like, do you know where that server is? Do you know where your application is? Do you know, like, you're like, in the cloud? I think that only works on like CEOs. I don't think that actually works when you like need to debug the production problem. So specifically, like, having servers, especially having cloud servers, especially having web applications architected the way that we architect almost all web applications nowadays when they're deployed in production, means that you have like a specific set of problems that are potentially screwing you, and you may not even know that it's happening. The biggest culprit here is routing. And that's kind of like a generic term. Like, if you have more than 1 app server, you have some kind of routing layer, right? Like, you have a load balancer, you are on Heroku and you use Heroku's router, you have big Cisco hardware boxes that cost hundreds of thousands of dollars and direct requests from your endpoint to all of your different app servers. I don't know. But how slow is that? Do you know? Like, do you monitor it? Can any of you tell me how long it takes a request to make it from a client to one of your app servers before the app server even starts working on it? Yeah. That was basically me not very long ago. Does your routing system back up? Like, do you have a way to know if that happens? Like, requests are coming in, that's a bottleneck, right? This is a single point of failure. Can you tell if you get too many requests and your load balancing system can't handle it? Like, will you even get an alert? Your application isn't going to have an error. It's never even going to see the request. You're just going to have clients who complain that your thing doesn't work, and you're not even going to like have a log trail to tell you why it didn't work, unless you do something else to make sure that you do. Figure this out because it's important. If you are like most people who deploy it yourself, you use probably HA proxy, the high availability proxy system. It does provide instrumentation hooks, and you can see if your routing load balancing system is backed up and how many connections it has and how many are waiting for an app server to open up. But even the most advanced people I know who watch that instrumentation page while they're deploying or whatever, none of those people have it hooked up to a graph. None of those people have it hooked up to an alert. Like, if your load balancer backs up, like, your end users are going to have a really bad time, and you won't know because you didn't get alerting about it, right? Maybe if you're lucky, one of the occasional pings from your uptime service will hit the timeout that your clients are hitting frequently. Maybe. Super related to the routing problem is overall request time. Like, you've instrumented your app, it's awesome. You don't even have averages, right? You have 95th percentile numbers on requests and how long it takes your app to respond to them. Super awesome, you are amazing. How did you manage that? You're ahead of everyone, right? That number is still basically lying to you. because that number doesn't start until after the entire load balancing system has finished. That number stops before the load balancing system spins back up to send your request back to the client. Like, you don't actually know how long it took that thing that your app took 20 milliseconds to render is going to take to get to the client. In my personal experience, on my super tiny response, like we send like, on average, our response sizes is like less than 5K of JSON. Our median response time is like 20 milliseconds. I'm like, fuck yeah, 20 milliseconds, that's amazing. It actually takes more like 300 milliseconds to make a round trip from a client, get that 20 millisecond response, and then get that 3K of JSON back to the client to get parsed. Like, just network, round trip, end to end. Like, that's more than an order of magnitude difference, and my mind was kind of blown when I discovered that that's what was actually happening versus what my application metrics were telling me was happening. Yeah, not your metrics. Like, in real life, what's your request response time? Basically, the only way to actually know the answer to this is to make requests to your application from all over the place and feed them into graphs. We run Heroku apps whose sole purpose is to make production requests in a loop and then send how long it took to our graphing system. That has a convenient side effect of telling us if routing is broken to somewhere in the world that we're testing from. It has a convenient side effect of telling us if lag gets significantly worse to somewhere in the world that we're testing from. But really, it's so that you'll know that your requests are taking a long time when you didn't think that they were. Super related to slowness that you probably weren't thinking about. Your runtime, which if you're like using Ruby, is the Ruby interpreter, right? Sometimes it stops. Like, how do you tell you've lost consciousness, right? If the VM pauses your running application to do garbage collection, say, it's just going to keep going once it's done, but it's not like your app is going to know that it was paused unless it's like doing clever things to watch for that. And especially if you're using Ruby or Python or some very high level language that's garbage collected, like, yes, you have runtime lag. Like, your garbage collector runs, your application is not doing useful things during that time. Do you know how bad your runtime lag is? Do you know how to track your runtime lag? So the solution that I totally stole from someone else and was just like blown away by how ingenious it was is every single one of our app servers, when it boots, spins up a thread that does nothing except call sleep1 in a loop and send to our metrics server how long it took to call sleep1. You're like, a second, right? No. Right? You actually measure how long it takes to call sleep1, and then you know how long your VM left you unconscious while that happened. Watching that graph not in an aggregate is super valuable because it means every once in a while I can say, that process has gone completely insane. Right? Like, that's really important. I wouldn't even know that that was happening. I would just know that my average time had gone up by 3 milliseconds, right? Like, is that actionable? No. Is knowing that a single Ruby VM has suddenly spiked to the point where it is lagging, say, 150 milliseconds per second. Yes, I can solve that. I can kill that process. My average response time will go back down, and I didn't have to like individually debug that problem. Honestly, I would never have individually debugged the average going up super slightly. Super related to runtime lag, VM lag. Do you run your application in a VM? Unless you host your own hardware, the answer is probably yes. Honestly, if you host your own hardware, the answer is still probably yes, because VMs make life a lot easier. Do you check for it? Do you know how to check for it? Do you know what it means? Like, if you get an instance, so I don't actually remember what cloud provider we were using, but I was contracting at a place where when we requisitioned a new VM to run app servers on, there was an order of magnitude performance difference between the fast newly requisitioned and spun up VMs and the slow newly requisitioned and spun up VMs. It meant that we could serve almost twice as much traffic from a fast VM. So we actually tested them, and we threw away the VMs that were on slow boxes. I could go on for a long time about why that happens and how that happens, but like if you have multiple virtual machines running on the same box, some of the virtual machines will be really greedy. Like you want to at least know if your boxes are sharing a box with a greedy VM, right? Like you don't want to be surprised that 30% of your app servers are as efficient as the remaining 2/3 of your app servers added together. Okay, so servers. Now let's talk about data stores in production. So data stores in production, unlike in development, are distributed. And I know like distributed data stores, that's not actually what I'm talking about. I'm talking about your database server is not your application server. That means that your data store is distributed. What does that mean? It means that you, having developed your application for many thousands of hours and finely tuned and honed your expectations for how talking to your data store is going to work, it means that everything that you know and expect from development is now wrong. A fire alarm again, that's reassuring. So let's start with saving data. So in development, when you say, hey, I have some data, and you tell your ORM or whatever, save this data, it tries to save your data. In development, your data's saved, right? Like that call returns and you're like, yes, my data is right there, I can see it. In production, saving data tries to save your data. Saving data might save your data, but they're not on the same box. Good luck. So some people who write data stores say that this is not actually something that you should worry about because your database server and your application servers will surely always be able to talk to each other because they are, say, in the same data center. Unfortunately, real-life experience indicates that network partitions and failures inside a single data center are super common, especially if you don't configure every single network thing correctly the first time. One of the times GitHub went down super dramatically and they couldn't get it back up for a day or two was because their backup networking system took down their primary networking system because of a misconfiguration. Everything was still there, but the database servers and the app servers couldn't talk to each other. And they didn't have a plan for how to make that not happen at that point. They do now. So having made it to the point where we now acknowledge that trying to save our data might not save our data, at least in production, you might think, oh, well, I know how to like solve the problem of data that might not be there. It's replication. We just need more copies of the data, and that will mean that everything will be fine. That is a great idea, and it can help with some kinds of problems. It does not save you from your data not actually being there later. So I could easily give multiple talks just about this. Super fast, there's an awesome guy called Kyle Kingsbury who has spent an insane amount of time doing experiments on data stores, figuring out how they handle network failures and figuring out how they handle replication failures and telling you whether or not the documentation for that data store is actually correct. I'm just going to cover what happens really fast with Postgres, Redis, and Mongo, and if you want details or you want to find out about any of the other maybe 6 databases that he's experimented on, his website is, I actually don't know how to pronounce it, aphyr.com. And he's written a series of blog posts called named after Carly Rae Jepsen. Here's my data, save it maybe. So Postgres. Postgres replication is asynchronous. You say, hey, Postgres, save my data. And Postgres says, got it, it's saved. And what it means is I saved it to my disk. The replicas, I'll get around to it sometime. Whenever. So the practical upshot of that is if there is a network failure, data that you know that you saved and that Postgres told you it saved and that your application has thinks is saved might not actually be there anymore. If that's okay with you, that's fine, right? Just be aware that that's the decision that you've made when you set up replication that way, right? Redis doesn't, by itself, Redis has replication, which has this effectively the same kind of replication problem that Postgres does, where it acknowledges the write before the write has replicated. But it also has no failover, so it's not actually a distributed database. It's just a follower. There is a thing by the author of Redis that is not fully complete, but that is functional, called Redis Sentinel, that actually turns Redis into a distributed database, or at least that's the goal. It elects a new leader if the previous leader disappears and does actually handle failover. Redis Sentinel has this interesting behavior where if some of your Redises can't see some of your other Redises, they each elect a new leader, and they each accept writes from whatever clients they can still see. And when the network partition ends, they elect a new leader, and whichever leader lost, I guess the good news is that one of the leaders' saved data is still there. The bad news is that the other leader's saved data has been completely thrown away. Right. This could be surprising to you if you think that a distributed data store means that your data from both places will still exist. Mongo has a really interesting default behavior of returning from your save request before the first node has saved the data. It says, hey, your network request completed, I'm done. This is tunable, but when you say, hey, Mongo, save my data, Mongo says done, and your data is actually on 0 places. So this is actually super easy to fix as long as you actually read the documentation on how to configure it. You say, I want to be able to survive however many nodes failing in my distributed data store. So tell Mongo that you need one more than that copies of the data in your distributed data store, and you'll be fine. It's actually pretty good. The kind of moral of this tiny story is trust no one. Even the people who wrote the database might be wrong about how it's going to act when it actually fails. If you personally didn't try the failure mode that you care about, you are just guessing what is going to happen, even if you have a piece of documentation that says what is going to happen. Try it. If you actually care about your data surviving, if some of your replicas can't talk to some of your other replicas, find out what happens. Again, the guy who does experiments on databases, Kyle Kingsbury, he has actually written a harness for testing data stores during failures, and it's kind of awesome if you want to automate it. This is a good way to try it for yourself if you care about being able to check. So, what did we learn? Production is fundamentally, systemically different. Development is not distributed. Development does not have almost any of the concerns that you have in production, other than hopefully it doesn't crash in either production or development. But production has a lot more concerns than that, and chances are high that you might have not thought about them yet. Failures in production are totally going to happen, but through a combination of, no, it's really not a combination. Through a combination of our own failures and other people's failures, we can learn how to resist failures in production. But the kind of moral of failure happening is don't have a failure happen and then be like, oh, I understand now. Production is just like development, except this one thing I had to change to make it stay up. That is not how it works. Production is different, and you need to expect it to be different. Don't create a pile of hacky fixes for the individual problems that you've already been bitten by. Surviving failure means having a system that is designed around the failures that you know that you care about. There are many failures, probably even failures that I talked about right here, that you don't actually care about. And those failures you don't have to think about, you don't have to plan for, it's totally fine. But some of these failures you probably do actually care about, and those are the ones where you should think about them, you should design for them, you should check on them, and you should test them. Production is not development. Don't you forget it.